All right, so now we're going to get into functions. And functions is actually a topic inside of precalculus that we're actually going to expand upon what you've learned in Algebra 1 and Algebra 2. So this is actually some really, really important information. The linear equations was really just kind of like that foundational stuff, making sure you remember like a line and all that kind of stuff. But for functions now, we're actually going to get into some really good like meat and potatoes of what you can expect coming into precalculus. So for these questions, we're going to graph the following functions and determine the domain and range. So when I want to graph a line, I usually just like to rewrite this in slope-intercept form. Okay, so y equals a mx plus b. All right, so to be able to do that, again, we're just going to basically solve for y. So I'm going to subtract the 2x. And we already kind of did this, but it's just really good to make sure you kind of go through the process here to make sure that you are not going to be making any mistakes and you remember everything and everything is kind of like automatic. So remember this -3 is going to divide into both of those. So therefore that's a 2/3. That's going to be 2/3 x minus 2. Therefore my slope in this case is going to be a 2/3 and my b, which again is my y-intercept, is going to be a -2. So we need to graph this and then we need to determine the domain and range. All right, so to go ahead and graph this, I'm just going to create a nice little x, y intercept. Remember, this is your x-intercept. That is your x-axis. That's your y-axis. So whenever you're graphing a line, you're always going to graph the y-intercept first. So we're going to go down to -2, right? And make a nice little dot. And then we're going to go ahead and follow our slope to another point. Remember, you only need 2 points to be able to graph the equation of a line. So the slope is that rise over run, right? The change in the y over the change in the x. So to graph this 2/3, I'm going to go up 2 and then to the right 3. 1, 2, 3. Now remember, when you have a positive slope, you could also have a -2 over a -3, right? So you could actually also go down 2 and then to the left 3. 1, 2, 3. Either way, you can see that all these lines or all these points are going to lie on this exact same line. So now let's go ahead and identify the domain and the range. So remember, the domain is a set of all x values that make up your graph. So you can see this graph is continuously expanding to the left as well as to the right. So the domain is going to be what we call all real numbers. So a couple different ways we can write, all real numbers. Obviously in precalculus, we get pretty heavy into interval notation, but that's something I want to deal with in precalculus. So for right now, I'm just going to use this R with the double line here to represent my all real numbers. You can also use interval notation like -infinity is less than or equal to x, which is less than or equal to infinity. And I'll kind of go through some of that interval notation as well. And the range is the set of all y values that make up the graph. And again, you can see that this graph is continuously expanding down as far as up. So the range is also going to be all real numbers. All right, now the next function that's really important is going to be this absolute value function. Now, to understand this absolute value function, it's kind of really important to understand what the parent graph looks like. And so let's just call the parent graph here g of x, and that's just going to be absolute of x. So that's going to be without any transformations. So if you remember from your study in Algebra 2, we kind of looked at this graph, and this graph took the shape of what we call like the V-shaped, right? So what the graph did is it looked something like this, and it went over that way, and it had this nice little point at the origin, which we call the vertex, which is at 0, 0. Now, before we kind of understand the transformations or what the new domain and range is of my function f of x, let's go ahead and make sure we understand what exactly the domain is of this function. So the domain, remember, is the set of all x values that make up this graph. And you can see this graph is expanding to the left as well as to the right. So my domain here is again going to be all real numbers. However, my range does not expand infinitely down as well as infinitely up, right? You can see the lowest point that my y value goes is going to be 0, right? It doesn't go below 0. So my range in this case is going to be for all y values that are greater than or equal to 0. Now we need to understand, well, what is this -2 and what is this -3 doing? So one of the things that we probably talked, or hopefully you talked about in Algebra 2, was looking at like the transformations, right? So f of x equals, you might have been familiar with this, x minus h and then plus k. And how did those impact our function? Well, remember, h was your horizontal transformation and k was your vertical transformation. So a lot of students will get it confused. If you recall, like if you go to my x minus 2, they'll say, oh, that's to the left 2. And actually it's the opposite. You're actually going to be moving to the right 2. So what I'm going to do, the reason why it's important to know this one point is rather than trying to like graph multiple points of my function, I can just take the one point I know and apply the transformation. So that's going to be shifted 2 units to the right. And then this -3, which is my k, is going to be your vertical translation. Now, when this is negative, you actually are going to go down that many units. So in this case, that's going to be going down 3 units. So now what I'm going to do is just kind of do my slopes. You remember that's over 1, up 1, like on either direction, right? So I can just kind of go like over 1, up 1, over 1, up 1. And I can do the same thing in this direction going from there. So you don't really need to be perfect. It's perfectly fine. Like there's no stretch or compressions. And again, for this video, I'm not going to be as like overly concerned right now as far as your shape of the graph. The main thing I want you to be able to understand is how to apply your transformations. Okay. And then also what's going to be the new domain and range. So what you can see here is though, this graph got shifted 2 units to the right and then 3 units down. Now what's important is this graph already had a domain that was all real numbers. So when I shifted this graph left or right, did anything change with the domain? And the answer is no. So the domain in this case is still going to be all real numbers. However, what about the range? Previously, the range only went as low as 0, but now when I shift this graph down 3 units, you can see now the lowest point of this graph is going to be a -3. So my range now is going to be y has to be greater than equal to a -3. Okay, now in the next function here, we have a square root function. So again, we need to understand what this parent graph is going to look like. So g of x is going to be the square root of x. And hopefully if you remember in algebra 1 or maybe even algebra 2, this graph is going to look something like this. Okay, so again, let's kind of understand what is the domain and range here. Now here you can see that the domain or the set of all values that make up this graph is not expanding infinitely to the left and to the right. Right? My domain is only x values that are greater than or equal to 0. Notice that's a filled in dot. That's why I use the equal to. And my range is exactly the same, right? The y values that make up this graph are all greater than or equal to 0. So y has to be greater than or equal to 0. So it's just really kind of important to recognize that they have the same domain, but no domain and range. But again, one's for x values, one's for y values, right? Okay, so a big mistake that students will make, and this happens all the time in pre-calculus because this comes up time and time again, is students will say, oh, 9 is 5, right? That's gonna, okay, it's not left 5, right? It has to be right 5. But that is incorrect. It's actually not going to be right 5. So what we need to understand is we have this 2 here. And what that 2 is actually doing is horizontally compressing the graph. Now, again, I'm not really going to be concerned about is your graph looking perfect, but I need you to understand that that horizontal compression is happening. And the reason why, kind of looks is one thing we might have, one thing we kind of talk about here is, your transformations of general functions. And so going away from the h and the k, which we use for quadratics and absolute value functions, another thing that we kind of look at is your b times x minus c plus a d, okay? And I kind of ran that off the side, so I'll make sure I include that over here. But the really important thing is I want you to understand is like your c, or this horizontal transformation, only makes sense when your horizontal compression is being factored out. So you can see here, this 2 is not factored out, right? It's just 2 times x minus 5. So to actually apply the proper transformation here, what I simply need to do is I need to factor out the 2 from the 2x as well as from the 5. So when I do that, what I'm going to be left with is a 2 times x minus a 5 halves. Now, a lot of times students will get confused here and they say, like, how did you do that? Like 2, you can't factor out a 2 from 5. 2 does not divide into 5. And you're right, it doesn't, at least evenly. However, like notice what happens when I like check my work. 2 times x is 2x. 2 times a negative 5 halves is going to give you a negative 5, right? So when you're factoring out something that's not divisible, you can just rewrite it and leave it into that factored form. So now we need to understand like, all right, what are these transformations then that's happening here? Like here's the graph. So now my graph is not shifting 5 units to the right. Do not make that mistake. The graph is shifting 5 halves to the right. All right. Now, again, going back to that one problem, if you remember in linear equations, like how do you graph something when it's a fraction? Well, just remember like 5 halves, right? We can rewrite that as a mixed number. 2 divides into 5, 2 times with a remainder of 1. So that's going to be 2 and 1/2. So let's go ahead and graph what this graph would look like. So again, I'm going to go ahead and draw this graph here. So there's my graph. It's being shifted over. This point is being shifted over 2.5 units. So 1, 2, 3. So 1, 2, and we'll go like 2.5. Now again, nothing's happening vertically, right? I'm not adding or subtracting anything. So the graph is going to stay there. Now you could say the graph is being horizontally compressed, right? So it's going to kind of look maybe like horizontally smushed. But again, it doesn't like, my main point that I'm trying to make is if it's smushed or if it's stretched, it doesn't really matter. Like the domain of this graph is still going to exactly be the same. Now the domain again is how far left does the graph go? How far right is the graph going? That is making up the graph. And in this example, you can see that the graph, I don't know why I did the interval notation here, I'm just going to leave it as an inequality, is going to be all x values that are greater than or equal to a 5 halves. And again, you can use a mixed number, but I prefer to use the improper fraction. Okay. Now, as far as my range goes, the range is unchanged. Like the only thing that happened was a horizontal shift, right? So when you just have a horizontal shift, the range is going to be what it originally was, which is going to be all y values that are greater than equal to 0, right? The range is only going to change when you have a horizontal or when you have a vertical change that was going on. Since there was no horizontal change, it was only horizontal. Since there was no vertical change, it was only horizontal, the range just remained the same. And that's actually supposed to be a 1, so that is incorrect. So the last one I want to do, and the reason why I know it was a 1 is because I was expecting, we're going to get into rational functions here later, but g of x equals a 1 over x. So it's important that students also recognize this function, which we call the reciprocal function. So if you kind of remember this one, this is going to be a pair of hyperbolas. And again, the important thing here is that we have some asymptotes, right? So this is that one function that we kind of introduced with asymptotes. And the graph looks something like this going in from there. Now, again, this is, another problem where you can see we actually have a b in front, right? So if you were to actually rewrite this, okay, you could rewrite this as a negative 1 times x plus 5. And again, you can see that we have a horizontal transformation, right? That plus 5, but again, we have this b. So what we simply need to do now is actually factor that out. So I'm going to factor out a negative. That's going to give me an x minus 5. Now, as far as this negative, you can leave it in the denominator, or you could also put it up top. There's a lot of different ways we could go ahead and write this problem. Now, if you put it in the bottom or in the top, it doesn't really matter. I don't want to get into the weeds because this is, again, something we're going to deal with more in depth in precalculus. But if you had it in the bottom, then that's going to be a reflection about the y-axis, and putting it up top is going to be a reflection about the x-axis. And again, it doesn't matter because if you look at this graph, this is what we call an odd function. If you reflected about the y, or if you reflect about the x, you're still going to get the exact same reflection that's going on, okay? So that's a kind of important thing. I'm just going to put it up top because that's typically how I like to see it. So what's going to happen is now this graph is being reflected about remember, there's a reflection that's going on, right? So the graph is being reflected about our x-axis, okay? So I'm going to flip this graph about the x-axis, and then what else do we have? Now we're shifting the graph 5 units to the right. So let's go ahead and graph what this graph is going to look like. So I'm going to draw my asymptote, though, is being shifted, right? So in this case, our points, or at least the things that we're going to apply with our transformation, are going to be our asymptote. So 1, 2, 3, 4, 5, I'm going to draw this new vertical asymptote. Now, the cool thing is, up and down horizontally or vertically, my vertical asymptote didn't change, right? The only thing that really happened was we were doing a horizontal shift. So now I just need to graph the reflection of this graph, which means it's going to basically be flipping. So this goes up here, that goes down there. So the graph is going to look something like that. Now let's go and talk about the domain. Now, as far as the domain, I'm not going to write this in interval notation because that's usually really confusing for students. I will just kind of do I'm just going to kind of do a set notation for this. So the domain, it looks like it's going to be defined. Looks like this graph is expanding to the left and to the right for all values except for the asymptote. So it's really true for all real numbers except for when x equals 5. So my domain, I'll say it's going to be true for all real numbers such that x cannot equal a 5. And why cannot equal 5? Well, because that's a vertical asymptote. All right. Now, as far as the range goes, we kind of have the same thing, right? It doesn't look, it's not defined at your horizontal asymptote. It looks like it's approaching that value from the left and from the right, but it's actually not crossing at any one of those values. So again, the y coordinates that make up this graph is going to be all real numbers except y cannot equal 0. So I'll go ahead and write this as all real numbers such that y cannot equal a 0. All right. So now let's go and get into the functions. Hopefully that was a good kind of little review of at least domain and range and like the graphs. Now the next thing is like the function notation. And just remember function notation, we have an f of x equals a rule, right? So the f is really just going to be the name. X is going to be your input value, right? And your rule is also sometimes called our output, right? So remember the input is going to be like your domain. The output from the rule is also going to be your range. Just kind of make a connection between those two. But one thing that's going to come up again and again is going to be evaluating, for our functions. So in this case, if I say p of 2, what I basically want to do then is be able to say, all right, well, what is the value of the function at 2? So what you're simply going to do is whenever you see an a, you're just going to replace that with a 2. So I'll have a negative 3 times 2. Okay, so negative 3 times 2, that's going to be absolute value of a negative, let's see, a negative 6, right? And the absolute value of a negative number here is just going to equal a positive 6. The next thing we can do is like operations. So you just remember, like we can also add, subtract, multiply, divide operations, as well as compose operations. So in this example, I have g of a, which is 2a minus 1, and f of a, which is an a squared plus a. So how would we subtract them? So, if you just kind of rewrite this, well, really g of a is equal to a 2a minus 1, right? So what I can do is I can just replace this with a 2a minus 1 and then minus an f of a, which is what? A squared plus a. Okay, now again, it's really important to notice I'm using parentheses here because again, you're not subtracting the a squared, you're subtracting an a squared plus a. So what I'm going to do is before I do any work, I'm going to get rid of my parentheses by distributing this negative. Over here, I don't really have any operations that's being applied to this. So therefore, I can actually just drop these grouping symbols. So therefore, I have a 2a minus 1. This would be a minus an a squared, and this would be a minus an a. Now, in this case, what you can simply do is just kind of rearrange everything. So therefore, everything's kind of grouped together. So this would be a negative a squared plus 2a minus an a minus a 1, okay? And 2a minus 1 is just going to be an a. So therefore, I have an a squared. Let's see, that's going to be what? A plus a minus 1. Now, composition is kind of a fun one because if you think about this, like if I did f of 2, like what would that be? Well, f of 2 is just going to be now a 2 squared plus 2, right? 2 squared is going to be a 4 plus 2, which is equal to a 6. So if I said, what is f of g of a? Well, I'm sorry, g of a, not g of x. Then what would you do? Well, then you'd say, all right, well, I'm just going to do a g of a, right? Quantity squared plus 2. Like whatever's as your input value, that's just simply what you're going to plug in to your function, right? So, I mean, it's like, it doesn't make any difference. It doesn't matter what whatever you're putting into your input value. Now, the cool thing is, though, we actually know what g of a is, right? We are given g of a. G of a is 2a minus 1. So, therefore, that's equal to a 2a minus 1 quantity squared, right? And then we're just going to be adding a 2, right? Or what was this, f of g of a? So, f of g of a, or it was f of a. I'm sorry, that would be incorrect over here. This would be a g of a squared plus a g of a. There we go. Okay, so then plus here is going to be what g of a is, which is a 2a minus 1. Okay, so now we need to remember, well, how do you multiply out a 2a minus 1? Well, remember, 2a minus 1 squared is a 2a minus 1 times a 2a minus 1. Do not distribute that squaring to both those terms. So what we actually need to do is multiply that out. So this is actually going to look like a 2a minus 1 times a 2a minus 1 plus a 2a minus 1. Okay, so very important that we have that kind of organized. And now what we can do is just go ahead and apply your distributive property here and multiply every term by every other term. I'll kind of move this to the left. 2a times a 2a is a 4a squared. 2a times negative 1, so that's a negative 2a. Negative 1 times 2a is going to be a negative 2a. And negative 1 times negative 1 is going to be a positive 1. And that's again plus a 2a minus 1. Okay, so now I can kind of group my terms. Notice how this negative 2a and this positive 2a, those are going to add to 0. They don't cancel out, they just add to 0, but that's why I'm kind of drawing the line here. The same thing's happening with the 1 and the negative 1. Those are going to add to 0. So therefore, I'm going to be finally left with a 4a squared minus a 2a. In the next example now, we're just going to do the same thing, but you can see it. Sometimes it can even get more confusing, right? What if I have this expression x plus h? So again, like do the same thing, like g of 2, what would that be? Well, if I said g of 2, then you do 6 times 2 minus 7, right? And so 6 times 2, that'd be a 12 minus a 7, which is just going to equal 5. And if I said, what about g of h of x or g of whatever? So what if I did a g of a x plus h? Again, just follow the process. You plug in a x plus h in for your input variable. In this case is x. That's going to be minus 7. Now, in this case, there's really nothing else I'm going to be able to kind of simplify here. 6 times x is 6x. 6 times h is going to be a 6h, and then that's going to be a minus 7. And that's kind of basically it. Like, we have multiple variables. It's just basically being able to apply that operation, or just being able to apply, substituting a value that's going to be most important. Now, another thing that we're actually going to spend a lot of time going further on in precalculus is finding the inverse. But I think it's just really important to kind of go through like the finding the inverse algorithm, just to kind of remember, because it is something that we talk about a little bit in algebra 2 that's going to be beneficial for you, because in precalculus we'll go through much more deeper kind of examples. So the important thing here to find the inverse is just replace your f of x with a y, right? And then what we're going to do is we're going to be swapping the variables. So x is going to equal a 5y plus 2, and now you're going to go ahead and solve for y. So I'll go ahead and subtract the 2. So I have an x minus 2 equals a 5y, and then you divide by 5, and you can say y is going to equal a x minus 2 over 5, right? Now again, this is the inverse, right? So we can rewrite this using like our inverse notation, and You can write that like -1 if it was an equation y, or you could also just say like f of inverse of x. So this little -1 up top. And then you could leave it like this, or you could also distribute the 5 to both of these terms, right? You could leave this as a x minus 2 over 5. You could rewrite this as a x over 5 minus a 2 over 5. Or a lot of times the preferred way we'd write this is a 1/5 x minus a 2/5, right? And you could write the slope and the intercept from there. Remember, a graph and its inverse are reflected about the y equals x line, and that's why we swap those coordinate points. Also, the domain and the range, if you remember, are swapped in that case. So this is a really important problem. You know, it actually comes up in calculus or in pre-calculus a lot, but I figured it'd probably be a good one to kind of cover here. Just again, to kind of work through that algebra, right? You replace g of x with y, and now what we're going to do is swap our variables. So x equals a 5y plus 2 over a y minus 1. Okay, now what we need to do is go ahead and solve for y. So how do we do that? And the reason why I wanted to cover this is because this is just really important as you're getting prepared for pre-calculus. This kind of like solving technique just comes really in handy. So if I have two y's, one's in the numerator, one's in the denominator, and you know I can't like divide them out or anything, what I need to do is get this y off the denominator. So I'm going to do that is by multiplying by y minus 1 on both sides. Then I'm going to go ahead and distribute here. So I'll have a xy minus an x, and those are going to divide out. So that's now going to leave me with a 5y plus a 2. Now again, I need to solve for y, right? So I need to get all my y's over to the same side. So what I'm going to do is I'm going to subtract a 5y on both sides. That's going to give me a xy minus a 5y. And then I will minus x equals a 2. I'll add an x to the both sides. So now I have a, let's just write over here, a xy minus a 5y equals a x plus 2. Okay, now again, I need to solve for y, and I have two of them, and I can't combine them, right? Those are not like terms, so you can't combine those two. You can't divide out the y. That's not going to work. So what you're actually going to want to do is factor out the y. See how these both share a y? You can actually factor that out. So when you factor out that y, you're going to be left with an x minus a 5 equals an x plus 2. Now you can solve for y by dividing by an x minus 5. And now you get the equation of y equals a x plus 2 all over a x minus 5. And then you can rewrite it in inverse notation. So g inverse of x is equal to a x plus 2 all over a x minus a 5.